Welcome to Homework Lib.
In this problem, we want to consider a hydrogen molecule, which is made up of two individual components, that has a moment of inertia 4.6 times 10 to the minus 48 kilogram meter squared. And the question asks us to find the wavelength of the photon absorbed whenever the hydrogen molecule makes a transition from the L3, which it's in right now, to the L equals 4 rotational level. So, since they've already given us the moment of inertia, we then need to consider the what equation we need to get eventually to a wavelength. So the first thing we need to do is think about the energy of a rotational system that has a quantum number L. So EL is equal to L plus 1 h bar squared all over 2I. And so if we take the fact that we're in L equals 3, transitioning to L equals 4, then we can find some delta E that is the difference between E4 and E3. So this works out to being 10 h bar squared minus 6 h bar squared. Oh, all over I should say. Sorry. Equals to 4 h bar squared over I. All right, so now comes the plugging and the chugging. So h bar squared is just a constant and I is given. So if you work this out, you get a delta E of 1.5 times 10 to the minus 2 electron volts. And then we can take the equivalency that the energy of a photon is given to us by Planck's constant times the speed of light over the wavelength of that, and plug in this value, our delta E, here, which gives us that our wavelength is equal to the delta E in the denominator of this equation. And if you work it out, you get to two significant digits, 82 micrometers. So, relatively large wavelength in the grand scheme of these atomic systems.